Every time a subway train applies its brakes, energy is wasted. Friction brakes take kinetic energy from the train's wheels and dissipate it as heat. And while current dynamic brakes recuperate some of this wasted energy, they don't stop trains completely, and they still leave some energy on the table. Here's a system I developed to significantly increase their efficiency. When building it, I had to consider both its ability to brake trains and its ability to recuperate energy. This is the hydroelectric generator loop. Like a squeezable yogurt tube, pressing on the bladder forces liquid through. The principle of braking is, as a train is approaching a station, the rolling brake engages the bladder and forces water through it. This energy has to come from somewhere, and it comes from the train, thereby slowing it down. My test showed that as we increase applied braking force, that is the downward pressure on the bladder by the brake, the train comes to both a quicker and shorter stop. By regulating this mechanically in real trains, we can allow them to brake effectively. The water is recycled at each end and flows through this DC generator where energy is recuperated as electricity. I'll be applying force to this bladder with this hand roller. We've hooked up the generator to this multimeter. We'll be measuring current. We set it at 10 milliamps. Let's see what happens. So the water that we pushed through here overloaded the multimeter. That's the current produced by this roll pushing water through that generator. Maximizing energy transfer between the train and the loop can make this a more efficient method of dynamic braking. An 80% train-to-loop energy transfer efficiency with an 85% efficient hydroelectric generator would mean a 68% net energy recuperation. Here is a concept of the brake. This is the brake, this is the bladder, this is a third rail on a subway train with comparison. This need not be as intrusive as my model suggests. It would only take up a portion of that train's undercarriage.